name's Felix. It's great to be here. It's great to see a room full of people. So that photo you took, Bruce, we're not going to have to sort of Photoshop American style to make it look a little bit more full. So yeah, today I'm going to be talking about WebGL, which you already know what that stands for. Some people think it's Web Graphics Library, but they're probably wrong. So this whole talk is going to be centered around this 3D model that I made a couple of years ago. You might recognize it as a Safari logo from Apple's browser. They actually changed how it looks in the newer versions, but the old version was this kind of shiny 3D looking thing. And I made this about 3 years ago, I think now, to kind of celebrate Apple finally shipping WebGL in their browser, which was kind of the last big step to allowing WebGL work sort of everywhere in mobile devices and on desktop browsers. Okay, so this talk is going to be split into 4 parts. And by the way, if these projectors cut anything off, or if they switch off completely, which they have done in the last 10 minutes, then you all need to shout, "Oh no," and then I know that they're broken, and I don't just carry on talking with a black screen, which I've done before. So I just want to practice now, okay? 1, 2, 3. Okay, good. I look forward to that not happening. Okay, so this talk's going to be in 4 parts. The first part is going to sort of handle what THREE.js actually is. Then I'm going to look into how I actually built this model here. So this isn't something which was made in some kind of rendering program like Maya or Blender. It's just made in JavaScript using code and put together. So it's not the best model in the world, but it's quite good as a sort of tool to learn how sort of 3D modeling works. Then I'm going to look at how you can take something like this and make it feel much more alive, because that's the whole point of rendering something in 3D, that we can interact with it, make it feel like it's actually a real object rather than it just being a static render. At that rate, we might as well just use an image and just load it the normal way. And finally, I'm going to look at sort of some of the things that are happening underneath the hood. So THREE.js is a library which lets you do things at a high level, but ultimately what it does is sort of does lots of interesting things on your graphics card. So I'm going to dig a little bit deeper and show how some of these things actually translate into commands on the graphics card. And this might sound scary and sort of very technical, but hopefully it'll give you some idea of how things work under the covers. Okay, so first of all, what is this THREE.js thing that I keep talking about? So THREE.js is probably one of the most popular libraries for creating 3D content on the web. And often people confuse it with WebGL. It's not the same thing. WebGL is what enables THREE.js to work. And THREE.js is basically this JavaScript library that takes WebGL and makes it a lot easier to use. It cuts out all of the sort of boring, complicated bits that you need to get the computer to draw what you want, and lets you focus on the higher level things, like I want to have a light here, I want to have a sphere here, that kind of thing. And if you want to check out some examples, this page here is the THREE.js homepage, which you can find at threejs.org. That's probably too small for you to see. And there's a bunch of interesting sites here that use THREE.js. But most interesting, I think, are these examples here, which show you lots and lots of different ways that you can build stuff yourself. So if you want to try something out, it's often good to take one of these examples as a starting point and then modify from there on. So just got a couple of these examples loaded up to show you what I'm talking about. So one of them is this more kind of artistic kind of toy where you have particles going about. And this mostly shows off that you can do something quite high performance using WebGL that you couldn't just do with JavaScript alone. Here we're showing lots and lots of particles animated, and if you were to just do this in JavaScript, it wouldn't run as fast. And when you're not using a projector, it runs a lot faster. I can tell you it's much more smooth. But this isn't really like a real world example. To show that WebGL isn't just like some toy that has got no real use, then another one of these examples is actually something that Ford have on their website as this car configurator, which lets a user sort of take a car, zoom around it, and basically customize it to get like a better idea of what's going on. And again, as with the previous demo, it runs a lot smoother if it's not on a projector. So it looks more impressive. Yeah, this is kind of in danger of crashing my computer, so I'll just leave it. And finally, the last one, just to show a bit about something what I'm working on. So my company called Procedural, we make these 3D models of locations. And this is all just running in WebGL, and at the moment it's pretty much frozen. But yeah, oh no, it does work. It does move around. So it's basically like a 3D map of a location, something like Google Earth, but rather than using satellite imagery from space or from aeroplanes, this is just using WebGL to create all of these textures on the fly. So all of this kind of snow terrain and all the trees are something that WebGL is drawing on every individual frame. Okay, so before I talk about THREE.js, I'd want to step back a bit and talk a little bit about WebGL, the underlying technology. So there's not really, at the base level, that much to understand. Essentially, WebGL lets you access your graphics card through the web browser. So you might have heard of OpenGL, which is a graphics library that lets you do this in native applications. And WebGL just takes this functionality and allows you to use it on the web. So that's all it is at a base level. It just lets you sort of access your graphics card, which before was something that you couldn't. In the past, it was a bit more problematic. Some browsers had it, some browsers didn't have it. But now pretty much every modern browser and every mobile device has got it to some extent. The performance does vary, but you can pretty much rely on it being there. And you might have also heard that now we actually have two versions of WebGL. So we have WebGL version 1, and now Chrome and Firefox are shipping WebGL version 2. And this essentially takes a lot of the features that were optional in version 1, which were kind of extensions, and puts them into the core. So we're really getting closer and closer to having something similar to native performance within our web applications. The reason I like using WebGL, as opposed to just, I don't know, programming in C++ or something like that, is because you get this quite nice, in my opinion, combination of JavaScript and GLSL. And JavaScript, I find like people can find a lot of things to complain about with JavaScript. Hopefully you guys don't all hate JavaScript, otherwise you wouldn't be at this conference. But I find it's quite a nice language for doing high-level expressive things with. You don't have to sort of make classes everywhere and implement protocols and all of that. Like if you just want to get creative, then you can play around with them. And at a high level, then this is something that's really good for the 3D. You can put things together using this language, which might not be the fastest language, but it's very expressive. And then if you want to implement something more high performance, then you can drop down onto the graphics card and use GLSL, which is the language that you use to implement these high performance visual effects. So you essentially have these two worlds, the kind of macroscopic high level world and then the microscopic GLSL world. Okay, so now onto THREE.js. So this is the library that is essentially powering everything that you see here in front of you. So within THREE.js, you kind of work with objects, and these objects get put onto a stage. And the kind of base level object is something called an object 3D, and this doesn't really do anything by itself. It's more the subclasses of object 3D that you manipulate and make do something. But every object 3D is, it's like you could imagine if you have a room, then in this room, each one of you would be an object 3D. And each of you have like a position, each of you have some kind of rotation, each of you have something that you're looking at. All of these kind of characteristics are baked into these object 3D objects. The ones that you actually see on screen are something called meshes. So these are objects which actually have data associated with them that describes their shape and also describing how they can be drawn. And specifically, these two things are called the geometry and the material of that mesh. So the geometry is just the collection of points which together describe your shape. So each one of you, like the shape of your hands, your heads, your legs, all of that would be some kind of geometry. And for, well, you're not all quite the same shape, but you're similar enough that we could probably share the same geometry between all of you. But you would probably all have slightly different materials. So the materials are the things that describe how, once you have a certain shape, how do you fill that shape in with colors? How does that shape react to light when it moves? Does it reflect light? Does it absorb it? That kind of thing. So once we have all these meshes, then we need to have some way of putting them together into some kind of cohesive whole. As I mentioned before, then meshes are just objects 3D, which can be positioned, rotated, scaled. All of these transformations can be applied to them. and you can group them together and then scale them. So it's sort of similar to when you have like a DOM tree and you sort of put things together to group. Oh no, yeah, there we go. What was I saying? Yeah, so you can group object 3Ds together just like you can in the DOM. Maybe I got punished for mentioning the DOM, which you should never do. Yeah, so you can group these together, and then you might have like 20 objects, and then you can move those as a whole and rotate them and scale them. And ultimately what you do is you take these objects and you add them onto a scene, which is like your root level object 3D. It's like your document that you add everything to. So once you have this scene, that's all great, but you need to actually somehow render it to a screen so the user can see it. So then you add this special object to the scene called a camera, like a camera that you have in the real world. And again, this can be positioned and different parameters can be applied to it. And this is your kind of view into the world. This actually captures all of your objects and transforms them into something that you can see. And once you have your camera, then you need something called a renderer, which actually does all this sort of processing for you behind the scenes and adds your actual final image onto the DOM. And once you have it there, then you're back into standard HTML, JavaScript, CSS. You can scale this, you can move it around the page, you can hide it, you can add transparency, you can add filters. All of this stuff just works. It's if you just had a little object. Okay, so this was all quite abstract, so I'd try and go into a little bit of code here to give you a bit more of an idea of how actually quite simple this is to put together with THREE.js. If you were doing this yourself with WebGL from the start, this would be pages and pages of code, and you'd all be asleep by now. So with THREE.js, it's made very, very easy and simple. So what I'm doing here, I'm just basically creating kind of one of the simplest possible objects, just a flat plane, so like as if it was like the floor in this room. So first I create a geometry, then I create a material, and then I combine them into a mesh like this and add them to the scene. Then I create a camera, and with all of these kind of objects, there's different types you could create, but the model is always roughly the same. So you create a camera, you add it to the scene, and then you create a renderer. So far you still don't actually have anything that you can see, so you need to then add that renderer's DOM element to the page. Once you have that, then you call render on the renderer, and your objects appear. So I touched on this a little bit earlier, like why I like THREE.js, but I just want to come back to it, because I do think it's kind of quite important. I'm trying to sort of persuade you here that you should give this a try, not just go like, oh, that's some kind of interesting, cool thing I heard at a conference. I actually think that it's actually a very rewarding thing to work with, all this WebGL THREE.js stuff. So the graphics, the 3D graphics is something that's very involved, and I did find it kind of confusing and scary at the beginning. But with THREE.js, you can really focus on this high-level content of, do I want to have lights or objects in my scene? How do I want them to move around? But then you can also drop into the really high-performance, quite interesting stuff, like what the graphics card is doing, and just play around with those effects yourself. And everything in between, those are the boring bits, or at least the kind of very confusing bits, then THREE.js handles for you. I mean, I often hear stories of people who've tried OpenGL and they tell me, I spent 2 days writing these commands, and at the end I just got a triangle, and that sucks. Yeah, that's the bit in between that THREE.js does for you, so you can focus on the creative parts. Okay, so now I'd like to go into how you can actually build something like this model. So we're going to look at some of the geometries and some of the materials that we use in this model. So this model isn't just like one big blob. It's actually sort of composed of different parts that you can stick together, rotate, and scale. And here I've just changed their position a bit to show how this thing fits together. So how do you go about creating a geometry? The model is pretty simple. You just create an object from THREE.js, and you just give it some parameters. And in general, the parameters are something that describe the shape. So here, the number 1 is just saying how big it's going to be. It's going to have a radius of, oh no, or 1. And then the 32 and 32 are kind of how high resolution the object is. So that was quite simple. A slightly more complicated object is a torus geometry, which is basically kind of like a ring. So you can think of this being formed as a circle that we kind of spin around its axis to give us this kind of like circular ring. And here again, the first two parameters are just describing the radius, so how big it is. We can get a little bit more complicated by defining shapes which are not some sort of primitive like a sphere, but rather here we're using something called a Lathe geometry. And what this lets us do is define a cross-section of an object and then spin it around its axis to give us something that looks 3D. So here we're doing something very simple. We're just taking 2 points, which are separated by some distance. That's this 0.1, sorry, this 0.1 here. And then these 2 points basically get spun around using this Lathe geometry to make this flat ring. So then we can apply the same trick to make the outer geometry of this compass. So this looks similar to the second geometry that I was showing you, but it's not quite just a circular ring. It's got a more kind of complicated path where on the inside it's got like a flat portion which the rest of the geometry sits upon. And this again is just defined by creating a path in THREE.js, extracting some points from it, and then creating a Lathe geometry. And I think finally, then we can make a text geometry. So this should be pretty self-explanatory. We just supply some text to THREE.js. We say how big we want it to be, and it will just create the correct vertices, the correct points that describe an object in 3D for us. Okay, so just been looking at geometries so far, but in my opinion, what's more interesting are the actual materials that we apply to our geometry. Because these are the things that really lets the object like feel like something real, something that responds to our user input to light, and that sort of things. So here what I have is just this object, and I'm just cycling through different materials on the outside to show the effect this has on the object. So the first material I want to look at is this wireframe material. So I had this in the other slides, and this is something which is mostly just used for debugging, so you can find out how your object actually looks at the vertex level, which can sometimes be hidden if you cover it in a solid color or something like that. And this can be useful to see how sort of dense your objects are and if you're perhaps wasting performance. So in this object here, then in the center, then we have this blob which is very kind of solid white, and there we're probably drawing too many vertices. We probably have too much detail there compared to the rest of the model. So it's probably worth reducing the resolution of that particular piece so our app runs faster. But onto materials that we'd actually want to use in our app. So the simplest one is something called a mesh basic material, and all you can do here is just specify a color. And then the renderer is just going to draw your geometry in one solid color, which looks pretty poor. This is kind of like the drawing a single triangle in OpenGL example, which everyone does and then gives up on 3D graphics. So you normally won't want to use something like this. You would more want to use something called a MeshPhongMaterial, which actually tries to simulate more than the previous material. So what this does is it takes in the position of the light in your scene, and it draws parts of the object which are closer to it in a lighter color and the ones which are further away in a darker color, and adds this kind of white glow on top of it, which your brain interprets to be like a 3D object, essentially. We can go one step further still, and rather than using the MeshPhongMaterial, we can use something called a MeshStandardMaterial, which is more sort of physically accurate. So before, we were defining this object in terms of sort of how shiny do we want to have it, but that isn't very sort of realistic. With the mesh material, what you can do is define how metallic the object is or how rough it is, and this is a more kind of natural workflow for sort of 3D modeling artists and the like. Okay, so far we've just been looking at solid colors, but to actually do something interesting, what we mostly want to do is take some kind of texture, some kind of image, and apply it to our object. And we can do this using textures, and there's actually quite different ways you can use textures within your scene. I'm just going to go over a few of them. So the simplest one is that we can just take this wood texture and apply it directly to our table. So we just kind of stick it directly on. And then what WebGL is going to do is when it's rendering the pixels that correspond to our table, it's going to look up into this texture and draw the correct colors based on that. So this is kind of like a direct application, and you can use with a MeshPhongMaterial or a MeshStandardMaterial. I'm trying to figure out. Hello? Yeah. I'm trying to figure out if there's like a special move that I do with my legs or my arms that triggers this being cut out and avoiding to do it, but I haven't got there yet. Yeah, so this texture can be applied to MeshPhongMaterials or MeshStandardMaterials. It's in addition to all the other things I was talking about before. So a more interesting way we can use textures is rather than using the textures to directly apply to the object itself, one example is we can use something called an environment map. So here we define a texture. I just used this picture of a sky that I took at some point. And we can say to THREE.js, imagine that this was the sky that was around our object, and then simulate a surface that is reflective. So then when THREE.js is rendering this object, then for every pixel, it shoots like an imaginary ray, which then reflects off our object and into the sky, and based on that, colors the object. And this is now giving us something which feels a lot more sort of real, a lot more metallic, and we're starting to get into this world where it actually makes sense to draw like a 3D object rather than just to have, you know, a sequence of images which you can click, 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 and spin around. So to go one step further, we can take an object which has got this environment map, so it's reflective, but we can modify how these reflections actually work. And we can do this using something called a bump map. So this is a texture which we use to describe how rough our surface is. So this looks something like this. It's just this kind of like noisy looking texture. And the color of each pixel describes how deep a bump is. So the black portions of this image are the holes in our material, and the white portions are the kind of the higher up bits. And when we apply this to our object, then here I'm kind of cycling through different levels of application of this bump map. So when we don't apply it at all, it's very smooth. But when we do apply it, then THREE.js kind of bends each of our reflections according to these bumps, and it gives this surface kind of like a sort of bumpy, textured look. Okay, the final piece to make this model into what it is that we need some kind of transparent looking materials. So something like glass to put on top of our compass. And to do this, we can just tell THREE.js that we want our material to be transparent, and we can then specify how. No, I'm really glad I said this "oh no" thing now. I thought it was going to be like not required, but it's been out 6 times now. Maybe we can have a competition with the different speakers. Yeah, you laugh. Yeah, with these transparent materials, we can specify things like reflectivity and opacity, and this kind of describes how much we can see into our model and stuff behind it. And with all of these materials and examples, it might seem to you like, oh wow, you just say it's reflective, then it's reflective, or oh wow, you say it's transparent. But actually behind the scenes to make this work is pretty complicated, and the fact that THREE.js just does this for you is pretty great. Okay, so that's how we kind of put this model together. How do we actually make it something that's animated? So I'm going to look at 2 things. So the first one is the lights, and this is something which really gives your brain a lot of clues as to the fact that this is a 3D object and that different parts of it are reflective, different parts of it are not, and that kind of thing. So lights are just like any other object 3D. You can just put them into the scene, move them, rotate them, point them at something. And here's just an example of creating a certain type of light, so a spotlight. Here you can specify a color and intensity, and then I'm just positioning it somewhere on the stage, telling it to look at a certain thing, and then telling it to cast shadows. And then as I move, as the app's kind of rendering, then I've actually made the light animate in this way. So the light itself is moving as well as the camera, and it gives this kind of effect of as if you had like a light above the object, which was kind of swinging left and right. Okay, so on to interactivity. So to make this something which is usable for the user and isn't just like one static render, we need to have some way of re-rendering our scene. So we need some way of calling code again and again and again. And one method that you might think of using for this is the set timeout function, which lets you schedule execution every sort of 50 milliseconds or something like that. Now, you don't want to do this. This is going to perform very, very badly and is going to annoy your users. Instead, what you want to do is use something called request animation frame, which is an API in the browser which basically tells your browser, I want you to tell me every time you're going to draw to the screen. So what this is going to do is it's just going to set up this loop for you, which is synchronized with drawing, with animations. And crucially, when you navigate away from a tab, this will stop calling. So you won't have your 3D model rendering again and again and again, even if you're not on the web page itself. So I just have an example here of how I would actually concretely move the camera, because it was a little bit abstract before. Essentially, the technique that you want to use is once you have your scene rendering again and again and again, then you want to have some kind of clock which tells you how long your application's been running, some kind of time. And then you want to use this time to derive some position for your camera. So the simplest one you could do is just say, at time equals 0, let's have the camera on the left side of the room. And then we just move it across 1 meter every second. So we say that the position is equal to the time. So what I'm doing here is a little bit more complicated. So I basically take the time here and apply some kind of scaling factor to it. And then I put it through a cosine function, which is a very useful way to make something that looks very kind of natural moving. So for those of you who've forgotten your high school maths, then a cosine function basically takes a value that's kind of going from 0 to something higher and turns it into something that's between 1 and 0. It's like if you were swinging on a swing. So then what this is going to do is essentially compute in our parameter r here, which stands for radius, a number which oscillates between a low number and a high number. So it's going to sort of zoom in and out. And then when it comes to actually rendering our app, then we take this position that we've calculated, and we can apply a bunch of other parameters to our camera to tell it to look up so it doesn't sort of twist to the side. And then we can tell it to look at a certain object. So this could be either like something in the scene, or we could have it follow something else that we were moving around. We could have it follow the mouse, for example. So this is what this actually looks like. I've made it a little bit more complicated. So I've taken this R parameter that I've computed, and I've added a kind of an orbital motion. So I now have the camera going round and round in circles around our object, but also zooming in and out. And this gives us this kind of nice fluid motion that doesn't seem too predictable to the user, but also isn't that hard to program. Now, another way that we can move the camera that isn't just calculated from time is by hooking into mouse and keyboard events. So here what I have is when I move the mouse from left to right, then it just moves the camera from left to right, and as I go up and down, then it just zooms in and out. And this gives the user just a nice way to play around with the object and feel like it is something that they can sort of interact with. And you can also interact with, say, like clicking or keyboard events or anything like that. Okay, so far this has all been talking about the high-level things, the kind of the easy parts, the JavaScript parts. So now I'd like to dive a little bit into what's actually happening on the graphics card. Just quickly check how much time I have. Okay, yeah, what's actually happening on the graphics card that actually lets all of this work. And this is quite complicated, so don't worry if you don't understand every single part of it. It's more just to give you some kind of flavor of what is actually happening lower down. So the graphics card is very different from the CPU that you have in your computers. It has a very kind of different model of computation. And rather than executing one single thread, it executes lots and lots of threads at the same time. So when it comes to drawing your screen, it doesn't go and calculate every pixel one after the other. It calculates maybe 100 or 200 at the same time, so it's very, very parallel. So the trick is basically writing functions which are going to execute very quickly, but given a different input, they're going to give a slightly different result. So they're all doing the same code, but they just take in different values. And to make our application work, we essentially need to write two programs which together form a shader. And a shader is what we basically call a program on the graphics card. And these are comprised of Vertex shaders. So these are programs which modify the actual geometry, and Fragment shaders. I'll just give two examples of these, just very, very basic, simple ones. So we write this in a language called GLSL, which looks something like this. And it's essentially a derivative of C. So if you know JavaScript, this should look reasonably familiar. And what these programs do is they essentially take some input. So here we take this A coordinate parameter, and they have to output something to this GL position. So this program is being run on every single vertex in the object on every single frame. And its job is to basically transform the description of the object that we have in JavaScript to something that is then drawn onto our screen. So all I'm doing here is just taking this parameter and outputting it. I'm not applying any transformation, not applying any rotation, no scaling. I'm just sending it through. So if we were to draw a vertex that had this A coordinate set to 0, 0, then that would end up in the middle of our screen. If we had one that was 1, 1, then it would be in the top right. It's not doing anything more than that. More kind of useful are these things called fragment shaders. So these are programs which get executed on every single pixel, in our image. And these don't output a position, but instead they output a color. So whereas before we were outputting this vector of 4 numbers which were corresponding to a position on the screen, now we're outputting red, green, blue, and alpha. So here, I basically wrote this simple program, which as you go from one vertex to another, it outputs a slightly different color. So the one part, and the kind of crucial parts of these programs that I haven't mentioned yet, is this varying parameter. So what does this do? So this is essentially a way that lets us pass data from the vertex shader to the fragment shader. And the way this works is that on every vertex, we specify some value for this varying parameter, this v coordinate. It could be a color, or it could be anything else. And then what the graphics card will do for us is it will automatically sort of interpolate this value for us between the vertices. So here I've basically said that I want this vertex to be the green vertex, this one to be the red one. And then as our pixels are drawn, then they'll get automatically blended between one and the other. So just to further explain this a bit more, I've got this diagram here which says how this program flow works together. So you basically have your program in JavaScript, which sends in these attributes which are describing your geometries. These are just like huge collections of numbers. These get passed into the vertex shader, which transforms them into the space of your screen. So it makes it look like a flat 2D image. And then the fragment shader goes and fills in these objects using these varying variables, which describe like how the colors or different parameters vary between the different parts. Okay, so to give you a demo of what this actually looks like, I'm just going to switch to Firefox, which has got quite a nice developer tool called a shader editor, which lets you actually dive in and look at what the shaders your app are using. So can you all see the text there? Is it too small? I'll take that as a yes. There's no oh no. If you can't see it, shout oh no. Yeah, so here I can select one of these programs and basically play around with it. So I'm going to go on this program which describes the outer ring, and then just take a look at this vertex shader that we have here. There's a lot of nonsense here which you don't want to focus on. It's very complicated. I'm just going to go to a point here where we have this parameter called transformed, which is kind of like our final calculated position. And what I can do here is basically take this parameter, which is describing the position of every vertex in this shape, and modify it. So what I'm going to do is just add 3 to it. And then what this does is it moves all of this object up higher above our scene. And this is like a fully fledged programming language. You can do all the kind of things you'd expect. So what I can do, for example, is only apply this to vertices which are in a certain region. So I can say if your x-coordinate is less than, say, 0, then apply this transformation. So now I've sort of selected only the pixels which are to the left of the origin and only moved those up. And you can kind of get more creative with this sort of stuff. So you can do transformations which, for example, don't depend just on like a static number, but I could use my, say, the sine function that I had before, and say if you're further away from the center, then modify your position based on this sine function. And I mean, this is just all fun and games. You wouldn't actually do this in real life. I'm just trying to illustrate how basically we have this same program that's getting executed on every single vertex, and it's all being done in parallel. So to show what the fragment shader is doing, I'm going to select the table. So which program is that? Yeah. So I'm going to select the table, and I'm going to go down again and find this frag color parameter. So this is what the final color of our object ends up looking like. So if I want, I can just go in here and say I'm going to set the red, green, blue of our frag color to be, if I just set it to 1, 0, 0, then this should end up being a solid red. And it's not, because I did it too early. Okay, so if I do it here, then yeah, then it just draws a solid red. And all of this program here is doing way more complicated calculations. It's calculating where the lights are coming from, all of these sort of things. But in the end, what it is really doing is just setting this parameter to be a certain color. And you can write your own shaders which do, well, any kind of host of things. And yes, to understand all of the stuff that THREE.js is doing here is complicated, but this does give you a sort of level of flexibility that you couldn't do within JavaScript. Like this kind of power, this kind of computational speed, you'd only get using the GPU. Okay. Yeah, so that's pretty much all I have. So I hope you enjoyed that, and I hope you enjoyed the rest of today. And I guess I'll go to some questions.
Thank you, Felix. Lots of questions for you, if I can find them on my Twitter. How's the unit testing experience for THREE.js apps? Are there any specialized frameworks that can help out?
Not so much, I think. I mean, it's all JavaScript, so you can definitely write tests yourself if you like. THREE.js itself has got some tests. It depends on what kind of unit tests you're talking about. I mean, if you're looking at trying to test the actual graphical side of things, then that, in my opinion, is something which unit tests are not very good for, because if a pixel changes, then you can't really compare it. But a lot of the other pieces, then you can write tests for in the same way that you could any other JavaScript app. Like, it is just JavaScript. It's not some crazy compiled C++ app or something like that. It is just like any other web application.
Also, do you know about the Vulkan APIs? I believe it's the next generation of OpenGL. Do you know if there's any porting of that to WebGL on the cards?
So yes, so Vulkan is kind of like the next evolution, for those of you who don't know, of sort of OpenGL. So you might have heard of Apple releasing Metal on iOS. So it's the same kind of thing for OpenGL. I think there has been some experimentation in Chrome to take this Vulkan API and expose it, but at the moment it's very far away. I wouldn't really rely on it coming to browsers for years to come. It took long enough to get WebGL to where it is, so I think it'll be some time until we get Vulkan.
Yeah, I mean, Apple are heavily promoting Metal, but
Yeah.
on the other hand, they did say they would never support WebGL, and eventually they did. So
Yeah, well, they did say they should never ship like a tablet, so they changed their mind.
it's almost like they lie to us, isn't it? Some old school questions. People wanting to know if they can export shapes or art from Maya or Blender into THREE.js. Is there any kind of exporting or universal format that you know of?
Yeah, so THREE.js has got a bunch of sort of importing modules, so you can import objects in an obj format or various other formats, like there's at least 10 or 12 of these. And these import both your shapes and your materials. So yes, you can definitely take something that you've made in Blender, export it directly into THREE.js. And I think Blender even has this function where it can export directly to THREE.js. So you make some object there, and it will just create a page for you that has all the libraries all set up, so you don't even have to do any JavaScript.
Wicked. Do you know if there's a store or somewhere where you can get ready-made shaders from?
I don't actually, I have to say. But that could be quite interesting. I mean, the shaders that come with THREE.js are pretty good, and especially in the examples, they have a bunch of other shaders that you might want to use. So THREE.js as a library tries to stay as small as possible, but then it has a lot of different examples which show you how you can add something on yourself. And there you have a bunch of different shaders, so ones that can help you do things like motion blur or making it black and white or pixelated, all of these sort of things.
Excellent. Ladies and gentlemen of Bucharest, please give it up for Felix Palmer.
Thanks.